Hello everyone, I'm Greg Karlovitz from the Hydrologic Engineering Center. Welcome to our course on statistical methods in hydrology. This video is part 4 of 4 on the topic of simple linear regression, and we'll discuss making predictions using linear models. Let's get started. Prediction is one of the payoffs for building a regression model. In many applications, the most important value is the best estimate for a new y, labeled y star, given some new value of x, labeled x star. Consider the following example from a topic that we've already seen. In regional skew studies, a regression model is sometimes used to estimate the coefficient of skew for flow frequency distributions over a large number of sites. Then, the model can be used to estimate the skew coefficient for a new site that was not included in the study. If the regression model uses drainage area above the gauge in square miles as the predictor, then to estimate the skew coefficient for the basin, you would take that basin's drainage area, put it into the least squares line as x star, and then get a value of y star, which is the best estimate of the skew coefficient for that basin. This is the most likely value of the skew coefficient for that basin given the model we built. We can say that this is the most likely value because of the distribution of the error terms and the conditional distribution of y given x. We have assumed and checked that they are normally distributed. The normal distribution has a mode, or most likely value, at its mean. We know that the errors have a mean of 0, so the most likely value from the model occurs when the error is 0. We know that according to the distribution of the residuals in our model, that the error in predicting with the model should be close to 0. However, the model still contains uncertainty because unless our model r squared is 1, there is still unexplained variability in our response variable. There are two things we're often interested in understanding once we've fit and checked our model. The first is the question of estimation. This asks, what is the mean value of the response variable y for the entire population that has a predictor value of x star? We're uncertain about the true value because of uncertainty in the parameters in our model. We talk about a range that contains the true value some percentage of the time and refer to that as a confidence interval. For example, we might say that the range 2.5 to 5.5 contains the population mean for a predictor value of 10 95% of the time. This would be the 95% confidence interval for the population mean given x star equals 10. The second question is that of prediction. This asks, what is the response of this specific outcome when its predictor is x star? We're uncertain about the true value because of uncertainty in the parameters in our model, but also the residual error. Again, we provide a range that contains the true value some percentage of the time, but in this case refer to it as a prediction interval. For example, we might say that the range 1.1 to 7.8 contains the true value of y for a predictor value of 10 95% of the time. This would be the 95% prediction interval for the response given x star equals 10. Typically, the prediction interval is the more useful of these two intervals, because we're usually more interested in the uncertainty in predicting a single outcome than we are in the population mean at a specific value. The confidence interval tells us how precise our estimate is of the mean response. We usually choose some significance level, for example 5%. Then, for that significance level, the corresponding width of the confidence interval contains the true population mean with a probability of 1 minus that significance level, in this case 95%. There's uncertainty in the mean response because of imperfect estimation of the regression coefficients. On the left is an example of how the confidence intervals around a least squares line looks. This shows the precision or confidence in our ability to estimate the mean response for any x star. Note that the intervals get narrowest at x star equal to the mean observed value of x and flare out from there. Note that this only talks about the uncertainty in the mean of the estimate, not about the range of hypothetical values that might occur. It's less sensitive to the assumption we made previously that the errors are normally distributed because we're not considering the residual error. The prediction interval gives a sense of precision on some yet to be observed x star. It's affected not only by uncertainty in the coefficients for the line, but also because the residual error comes into play as well. Recall that the full regression equation contains not only the least squares line, but also the additive error term on the end. The plot on the right shows the prediction interval for all x star. What you can see is that it minimizes at the mean of x and expands outward from there. Note that in comparison to the confidence intervals on the left, that the prediction intervals are much wider. This is because the first one does not include residual error, but the second one does. It's much more sensitive to the assumption we made previously that the errors are normally distributed because the residual error is now included. Here are the equations for computing the confidence interval and prediction interval. I want you to get a conceptual feel for these because in practice, software like R will compute these for you. They are similar with one key difference. The intervals are centered at the same value, which is the value of the least squares line at x star, except we interpret these intervals differently and use a different symbol to represent where the center of the interval is. What I want to bring to your attention are t and the form of the expression under the radical. The t value is a critical value t statistic for the selected significance level. You will choose how wide of an interval that you want in terms of a percentage, for example, 95% coverage. Then, based on the sample size n, you'll consult your trusty t table and find the associated t statistic. This sets how wide the interval will be based on your selected coverage. Nowadays, we usually use software to compute this for us, but many of us have spent years looking at the tables in the front or back of our statistics textbooks to go hunting for our t values. Let's assume our selected confidence level is 95% and our model sample size is 9. This means we're looking at the sixth column of this table. Our number of degrees of freedom is 7 because we lose 1 each for estimating the intercept and coefficient of the model, so n minus 2 equals 7. Our resulting t value is 2.365. Now let's look at what makes these two intervals different. The key difference is underneath the radical. The confidence interval does not have the 1, but the prediction interval does. The impact of this is that the prediction interval will always be wider because there's more uncertainty associated with predicting a random variable than with estimating a fixed parameter. The population mean is a fixed parameter. The outcome of y star for a given x star is a random variable. Normally when we're modeling, we're in an environment that makes predictions straightforward. In R, once you have your model fit to some data and you've checked your assumptions, you can make predictions by passing your fitted regression model to the predict function. The predict function takes an extra parameter called new data that asks you where you want to make the predictions. It also lets you set what kind of interval you want, with none providing the best estimate. It lets you set the significance level as well, although the default value of 0.95 is generally fine to use. There are several other options that you can accept the defaults on. Here's the function in action. Don't worry if you're not familiar with R yet. The workshop on this material will give you time to learn how some of these R functions work. The first is an example of the prediction interval. The name of our model fit object is model1, and then we give it a data frame with a new value for our predictor value. The new value is 1000, so the predictions will be made at x star equals 1000. We ask it for the 95% prediction interval, remembering that the default value is 95%. The result has 3 values: the fitted value or best estimate, the lower prediction interval, and the upper prediction interval. Then for comparison's sake, we also ask it for the confidence interval at x star equals 1000. Note how everything else is the same, except we switch the interval argument to confidence. The result is printed on the next line. Note how much narrower the interval is. We haven't switched the confidence level for this. It's still 95%, but remember that the confidence interval will always be narrower than the prediction interval. In this video, we discussed making predictions using linear models. The key points to take away from this video are: once a model has been fit to data and checked, it can be used to make several types of inferences. We can make a best estimate of a response variable given a value of a predictor variable. We can estimate the confidence interval of the population mean for a response given the value of a predictor variable, and we can estimate the prediction interval for a yet unseen response given a value of a predictor variable. Thanks, and come back soon to learn about other topics in our statistical methods and hydrology course.